Why are odd Bernoulli numbers for k greater than 1 0? So basically b of 1 is minus 1 by 2, yeah, so this one is not 0, but all other odd Bernoulli numbers are actually 0. So in this video let's try to prove this fact. Yeah, so in my previous video, which I have linked over here, I discussed about the generating function for Bernoulli numbers. Yeah, so basically this was given by Euler, and basically if we have x by e to the power x minus 1, this is actually equals to sum going from n equals to 0 to infinity, Bernoulli of n by n factorial x to the power n. So you can see that its derivative evaluated at 0 are exactly the Bernoulli numbers. If we take the derivative of this expression, let me show you like if this is true or not, like just for the sake of giving you the idea that it's true. So let's do it for let's do it for the 0th derivative and then for first derivative, and then we will see if that's actually correct or not. So now f of 0 is just 0 by e to the power 0 minus 1. So this is in the form of 0 by 0. Yeah, that's why we need to take limit. Now if we take limit x tends to 0 of x by e to the power x minus 1, this is limit x tends to 0, not a derivative, 1 by e to the power x. So this is just 1. Yeah, so that's why our b of 0 is 1. Yeah, and since it's Taylor series, sorry, Maclaurin series, so that's why we have n factorial and x to the power n, and this is actually the nth derivative evaluated at 0. Yeah, we know that. Now let's try to find f dash x. Our f dash x is b u dash minus u p dash by b square. Yeah, so we have basically this expression e to the power x minus x e to the power x minus 1, is it? Yeah, and then by e to the power x minus 1 whole square. Now f dash of 0 is, this is 1 minus 0 minus 1. Again we need to take L'Hopital's rule because this over here is 1 minus 1, which is 0 by 0 form. Now if we use limit again to find this expression, what will we get? So limit x tends to 0 for e to the power x minus x e to the power x minus 1 by e to the power x minus 1 whole square. Since it's in the form of 0 by 0, we take L'Hopital's rule. That's why we have limit x tends to 0 e to the power x minus, this is x e to the power x plus e to the power x by, this over here is 2 times e to the power x minus 1 times e to the power x. Now divide by e to the power x, that gives us x to the power 0, 1 minus x plus 1 by 2 times e to the power x minus 1. Now this is just limit x tends to 0. Yeah, so this is not plus 1, this is minus 1 actually. So minus x, yeah, by 2 times e to the power x minus 1. Now this limit over here, if we take minus 1 by 2 out, this limit is already over here and this is 1, so we have minus 1 by 2. So we see that this first derivative evaluated at 0 is actually minus 1 by 2. So that's why now b of 1 is actually minus 1 by 2. Now with this you might have got some idea that this is actually true. Yeah, you can also evaluate for others, second derivative, third derivative, and you will just get that b of 2 is 1 by 6, b of 3 is 0, b of 4 is 1 minus 1 by 30, and so on. Okay, so Now you are convinced that this Taylor expansion, or let's say Maclaurin expansion, or generating function by this polynomial is true. Now let us try to prove why for all odd numbers, why the Bernoulli number is 0 for all the odd numbers greater than 1. Yeah. Now this will also show us the beauty of mathematics. Yeah. So let me show you how. We have x by e to the power x minus 1 as sum from n equals to 0 to infinity b to the power n by n factorial x to the power n. Yeah. Now let us take out the term for n equals to 1 from this series. So what I mean by that is, so when n equals to 1, we have b1 by 1 factorial times x. Yeah. So let's take that out from the sum. N equals to 0. What I can write is from from infinity, but n is not equals to 1. Okay, so this is the condition now. We have bn by n factorial x to the power n. Yeah. Now b of 1 is just minus 1 by 2. I can take that to other side. We have x by e to the power x minus 1. So there we have 1 by 2 times x. So n is greater than equals to 0, but n is not equals to 1. I can write like this as well. So we have bn by not 2 n factorial x to the power n. Okay, now how can I write this? Okay, so I can write this as I will try to show this as even function. Yeah. Okay, so now for that I can write this as 2x plus, now this is x e to the power x minus 1. Yeah, and this is over here bracket. So we have sum and greater than equals to 0 and not equals to 1 bn by n factorial x to the power n. Now what I can do, so basically here's x to the power x minus x, so that gives me x plus x to the power x. Yeah, I can write this like this because the minus x, it's over here. Now I can take x common, so that gives me x 1 plus e to the power x by 2 times e to the power x minus 1. Yeah, okay, this is just some manipulations that will help in some time. Yeah, let me I will show you. Now after this, what we can do is we can basically divide numerator and denominator by e to the power minus x. Okay, so I think you are familiar with these expressions as well, because now it's e to the power x by 2 plus e to the power minus x by 2 by e to the power x by 2 minus e to the power minus x by 2. I think you know this expression as well. This is just cot as x by 2. Yeah, and this has also a lot of implications for proving the values for Riemann zeta of 2x and all other stuffs, but that's for another time. Now we can modify this like this, yeah, by dividing by e to the power x by 2. Yeah, so we have equals to summation from n greater than equals to 0 and is not equals to 1, this sum bn by n factorial x to the power n. Yeah, so now what I want to show is, let's say I want to find this sum, and now we know that odd numbers, for odd numbers it should be 0. Yeah, so let's see like how the math considers true thing as always true, and like how it will help us in proving. Let's say I want to find for minus x to the power n. Let's replace x by minus x, and let's see how does this go. So basically here's also we have minus x by 2 and e to the power x by 2 plus e to the power minus x by 2 by e to the power x by 2 minus, okay, now this changes to minus, this changes to plus, this changes to minus, this changes to plus. Okay, now the minus sign over here again changes the order of this sum. So we have x by 2. Now we can write this as e to the power x by 2 plus e to the power minus x by 2 by, and this will be e to the power x by 2 minus e to the power minus x by 2. Yeah, we have used this negative sign over here. Now this is just the original series. Yeah, so this is actually equals to sum and greater than equals to 0 and not equals to 1. So bn by n factorial x to the power n. Okay, now for this I can write this as sum from n greater than equals to 0 and not equals to 1 bn by n factorial minus 1 to the power n x to the power n. Okay, so now since both of them are equal and all the coefficients of the corresponding powers of x, let's say the terms involving x square and x square, terms involving x cube and x cube, terms involving x to the power n and x to the power n, this should be same. Yeah, so that's why the terms involving x to the power n are bn by n factorial minus 1 to the power n. This should be equal to bn by n factorial. Now n factorial cancels out. Yeah, so now if n is even, this will be automatically true because minus 1 to the power even numbers is bn equals to bn. Now if n is odd, in that case we have minus bn equals to bn. Yeah, so that implies 2 times bn equals to 0. Yeah, that implies bn equals to 0. And note that, like, one of the amazing things that I found out during this proof is, so basically when we exclude the case where n was 1, so this function turned into such a way that this was an even function. Yeah, so basically for all other numbers this series had to have all numbers at 0. Yeah, and so that's why to make that true, the right hand side, or let's say this is left hand side, turned out to be an even function because the right hand side had to have odd numbers at 0. So yeah, so math is automatically doing correct things something like that. So basically due to taking out the only case where it was not 0, we got a function where this was even, and due to the evenness of this function we got that bn minus 1 to the power n equals to bn, and for odd numbers we had negative bn equals to bn, so 2 times bn equals to 0, so bn equals to 0. So that means that if when n is odd and n is not equals to 1, our bn will be 0. And we proved this, yeah, simply by excluding a case and then turning it into even function. And the thing that this over here is just caught as function will have great implications for us in the future. Yeah, and yeah, hope you enjoyed this proof, and I have given the credit of the proof to its owner, who is Arizona planetmath.org. I got this proof over there and I was extremely overwhelmed, so I thought of sharing with you guys. Hope you enjoyed the proof, and hope you enjoy this thing as well, where I try to give you an idea that this is actually true. Yeah, and yeah, Euler is great. Thanks for watching. Look forward to seeing the upcoming videos too.